Imagine taking a handful of ordinary photos, then flying a camera through the scene as if a full 3D movie set had been rebuilt behind them. That is the magic behind Neural Radiance Fields, often called NeRFs. A normal photo is only one frozen viewpoint. It tells us what light reached the camera from one position at one moment. It does not directly tell us what is hidden behind a chair, how deep the table is, or what the room looks like from the other side. NeRF asks a simple but powerful question. If we collect many photos from different angles, can a machine learn the invisible 3D structure that must have produced those images? Not by hand modeling every surface, but by learning how light behaves inside the space. Traditional 3D graphics often use meshes. A mesh is like a digital sculpture made from connected triangles. NeRFs are different. They do not start by drawing triangles. They learn a field, which is more like an invisible cloud of information filling the scene. A field is just a value everywhere in space. A weather map can have temperature at every location. A magnetic field has strength and direction around a magnet. A radiance field stores how much light appears to come from each point when viewed from different directions. To understand NeRF, follow one pixel backward. A pixel in a photo was created by light traveling along a ray into the camera. That ray passed through the scene. It may have hit a wall, crossed empty air, or picked up color from a shiny surface. Now multiply that idea by millions of pixels across many photos. Each pixel becomes a tiny clue about what exists along one path through space. NeRF training is the process of making one consistent 3D explanation that agrees with all those clues at once. At each sampled point in space, the NeRF model tries to answer two questions. How dense is this point? Meaning, how likely is it to block or absorb light? And what color would this point appear from a particular viewing direction? Density is the model's way of saying whether something is really there. Empty air should have almost no density. The surface of a mug should have high density. A soft edge, like smoke or leaves, may be spread out rather than perfectly sharp. Color is not always the same from every direction. A matte wall looks fairly stable, but a glossy table can flash brighter from one angle. By giving the model viewing direction, NeRF can learn some of these view-dependent effects instead of treating the world like flat paint. The word neural means a neural network is used as the memory for this field. You give it a 3D location and a viewing direction. It returns density and color. In a sense, the scene is compressed into the learned behavior of that network. If this kind of visual explanation helps you understand future technology without the hype, consider subscribing. We are going to keep building the idea step by step because NeRFs are one of those topics that become surprisingly clear once the picture clicks. At the beginning, the model does not know the scene. It is like a painter guessing in the dark. It samples points along camera rays, predicts colors and densities, and combines them into a fake version of each training photo. Then the system compares the fake photo to the real photo. If a pixel is too dark, too bright, or the wrong color, the network is adjusted. This happens again and again until the rendered views become close to the original images. This is important because nobody has to label every chair leg, window, or plant leaf by hand. The photos supervise the model automatically. The only target is simple. When viewed from the known camera positions, the learned field should reproduce the photographs. For this to work, the system usually needs to know where each photo was taken and which way the camera was facing. Many pipelines estimate this using structure from motion, which matches visual features across photos to recover camera positions and a sparse set of 3D points. Overlap is the friend of reconstruction. If the same window corner appears in 10 photos, the system can triangulate where it probably sits in space. If an object appears only once, there is much less evidence, and the model may have to guess. Once training is done, we can place a virtual camera somewhere new. For every pixel in that new view, the system casts a ray into the learned field, samples points along it, and blends their predicted colors according to their densities. Think of looking through layers of colored glass. Near-dense layers matter more because they block what is behind them. Empty space contributes almost nothing. NeRF rendering uses this kind of volume blending to decide the final color of each pixel. The result can feel cinematic because the model has learned more than a flat panorama. As the viewpoint moves, foreground objects shift against the background. Hidden surfaces may come into view. Reflections and soft edges can change in ways that feel spatial. Parallax is one of the biggest clues that your brain is seeing 3D. Hold up your finger and move your head. Your finger seems to slide against the background. NeRFs aim to create that same effect from learned scene structure. A 360-degree panorama can look impressive, but it usually assumes your eye stays in one place. Move too far and the illusion breaks. A NeRF is built for new viewpoints, so the camera can shift through space instead of only rotating in place. Photogrammetry often tries to recover explicit surfaces and textures. That can be excellent for solid objects. NeRF focuses on recreating how the scene looks from new views. It can handle delicate appearance effects, but extracting a clean, editable mesh is not always straightforward. The beautiful part of NeRF is also the expensive part. To render one image, the system may need many samples along many rays. Early NeRF methods were known for impressive quality, but not instant speed. Later research has focused heavily on making them faster. Many improvements use clever data structures, grids, caches, or alternative scene representations, so the system does not waste effort in empty space. The principle remains similar. Learn a representation that can explain the photos, then render new views from it. One popular family of related methods uses many soft 3D blobs called Gaussians instead of storing the scene only inside a neural network. These blobs can be rendered very quickly and still act like a radiance field. The goal is still new view synthesis from images. NeRFs do not magically know everything. If no camera ever sees behind a cabinet, the model cannot truly reconstruct the hidden back wall. It may fill gaps in a plausible way, but that is not the same as measured reality. Classic NeRF works best when the scene is mostly static. If people walk through the shot, leaves blow in the wind, or lighting changes dramatically, the model receives conflicting evidence. Special dynamic methods exist, but motion makes the problem harder. Reflective glass, mirrors, water, and transparent objects can also be difficult. They show light from somewhere else, not just the surface itself. NeRFs can learn some view-dependent appearance, but perfect physical understanding of reflections is a much deeper challenge. Good reconstruction depends on good coverage. Photos should see the subject from enough angles, with enough overlap, and with limited blur. The model is not only learning from images, it is learning from the paths that connect cameras, pixels, and the scene. Picture a museum artifact photographed from every side. A NeRF-style reconstruction could let a viewer drift around it, inspect carvings, and see subtle lighting changes. This does not replace the real object, but it creates a richer digital window than a flat photo gallery. Now imagine an apartment listing. A normal photo shows one angle of a room. A panorama lets you spin your view. A radiance field could make the walkthrough feel more spatial, because you can shift your viewpoint and sense the true layout more naturally. For robots and autonomous systems, the idea is not just pretty rendering. A scene representation that connects images, geometry, and visibility can help machines reason about where objects are and what a new viewpoint might reveal. The visual world becomes more queryable. A common misunderstanding is that NeRF simply converts photos into a normal 3D file. It is better to think of it as a learned scene renderer. It can produce new images from new cameras, but editing, measuring, or simulating physics may require extra steps. NeRF matters because it changes the relationship between photography and 3D. A photo used to be a flat record of light. With enough views and the right model, photos can become evidence for a navigable world. That is a major shift for media, memory, design, and simulation. The core idea is beautifully simple. Learn what light would look like at every point from every direction that matters. Use real photos as the teacher, then ask new camera rays what they would see. That is how AI can rebuild the feeling of 3D worlds from 2D images. What part of NeRFs would you like explained next? The math of volume rendering? The difference between NeRF and Gaussian splatting? Or how this connects to virtual world and robotics? Ask your question in the comments and suggest the next future technology topic.